Morning. So over the last couple months, the internet's seen a number of rather significant just DNS reflector attacks that have targeted a number of people. At VeriSign, we've had an opportunity to collect a lot of data on it, both from a victim and a reflector point of view, and that's what I'm going to talk about here today. So the first thing we need to talk about is what the attack actually looks like. And basically the way that someone perpetrates this attack is an attacker will break into an innocent authoritative DNS name server somewhere out on the internet and publish a large text record. Then they'll use a set of zombies or otherwise owned boxes to send queries to an army of reflective open DNS servers. And they'll send those queries with a spoof source address of the victim that they want to attack. And that victim will get buried under large DNS responses that were generated with very small queries. If we look at what the victim typically sees in an attack like this, it's a lot of traffic. This is a net flow graph of an attack that we have the opportunity to analyze. This is a 1% net flow, so it's actually 2.2 gig of traffic, and we were able to work with our ISPs and figure out that there's actually an additional 3 gig that never even made it to the site. So it was in total a 5 gig attack. When we looked at the actual traffic, they were all answers for e.tn.co.za. It was a 4,028 byte response. It was generated with a 64 byte query, which is about 63 to 1 amplification, using about 34,000 reflectors. This is a net flow graph of our source and destination addresses talking to the data center that was attacked, and you can see the spike of about 30,000. We looked at TTL histograms to make sure the traffic was actually coming from the reflectors it looked like it was coming from, and it was. We looked at the reflector list, and it was very obviously the output of a sequential scan. It was 18/8s right in a row that the IPs came out of. We randomly sampled them, sent them DNS queries, and they all answer recursively. 5 gigs of traffic from 34,000 reflectors is an average of 144 kilobits per reflector, or an average of about 13.5 packets per second, or 4.5 DNS queries per second. When you look at the 63 to 1 amplification, that's about 2 kilobits per second on the inbound side per reflector. So if you're talking about the reflector operator seeing 2 kilobits per second of traffic on the inbound side and 144 kilobits of traffic on the outbound side, it's pretty unlikely that a reflector operator is ever going to notice that this is happening. We looked at a capture file during the attack to make sure that there wasn't a small set of top talking reflectors that were burying the victim with traffic, and everybody else was just noise. But it turns out that the top talker was only sending 8.5 responses per second, which is pretty close to the average that we anticipated. As a reflected attack, we can't really do any analysis on the headers of the packets to determine if it's coming from one source, multiple sources. We can't tell anything about the person originating the attack, but we can estimate the origination traffic by taking the total traffic volume and dividing out the amplification factor. And we think that this 5 gig attack traffic was generated by less than 79 megabits of initiating traffic, which means 5 gig DDoS could have been generated by a single well-connected host in a data center. In the case of this attack, we were able to work with the appropriate registry, ISP, and eventually got the owner of the DNS server on the phone. We were able to confirm that it was a DNS server that was owned and the record was maliciously installed. It wasn't something that actually belonged in the DNS tree. Interestingly, this domain had 2 authoritative name servers, only one of which had been compromised. So the attack traffic was 65% responses and 35% name errors. Because the packet is so large, it gets broken up into 3 fragments, and the attacker sets the destination of the port of the attack by setting the source port for the queries that they send out. The particular attack that we studied was 24 minutes in duration, and if we look at this graph, that's the graph of the destination ports that were used during the attack, and you can see it came in 3 phases. The blue is destination port 666, the yellow is 53, and you can see it started out as all 666, then shifted to split between 666 and 53, and then it shifted to all port 53. If you look at the graph, you can see that the shifts are nearly vertical. The start was nearly instant, the stop was nearly instant, and the changes were nearly instant, which indicates a pretty tight command and control over the origination of this. So a lot of talk has gone on in various forums about what victims can do for filtering techniques. One of the things that's been discussed is filtering out open recursive DNS servers. The problem is how do you put an ACL on a router to block 500,000/32s, and even if you want to do it with a black hole route server, that's an awful lot of routes to be able to handle. Not to mention, you will have just broken 500,000 DNS servers that, if you're a root and TLD operator, are the people who need to talk to you the most. Discussion's been had about limiting DNS packet sizes to 512 bytes by default. That would break a lot of things because there's more and more technologies coming out that we'll talk about later that depend on large records in the public DNS tree. People have talked about stop transiting port 53 across the core of the internet and force hierarchical DNS model. We think that would break a lot of things with DNS. One thing that we found works pretty well is dropping fragments towards the victim, but you have to make sure that your victim should never actually receive a fragment coming towards it, which works if you're a DNS operator. whatever technique you come up with, whatever fancy filtering scheme you come up with that will drop the traffic, one of the other challenges is that you have to get your ISP to implement it unless you've got an extra 5 to 10 gig of capacity to absorb the attack and filter it yourself. Some of the challenges with that are the ISP hardware doesn't always have good filtering features in the line cards. We've called ISPs before and said, hey, can you drop fragments towards us? And we're told, nope, our hardware doesn't support it. Some ISPs won't filter the packet if they don't see live, won't put ACLs in place if they don't see live attack packets. When you're talking about a 24-minute attack, it's pretty hard to get the ISP on the phone in that duration. And then when you do get them on the phone, sometimes they won't leave the filters in place, which means you're free to get knocked down again a week later. And if you do get them to leave it in place, it's catch-22 because now you have no idea when you are or aren't getting attacked. So we were able to get a query log off of a reflector and do some analysis on that. The query log we had was from January 11th through February 27th of this year. And this is a graph of the attack queries per second that reflector saw. And you can see the numbers are pretty consistent with what we figured the averages would be based on the attack that we analyzed. If we take that number and multiply it by 4 kilobit text record, which most of the attacks use, times 8 bits per byte, we can extrapolate the bandwidth that the average the reflector that we studied was sending out, and we can see again it was consistent with the averages. So if we look at it from a 10,000-foot level, between January 11th and February 27th, this single reflector sent out 1.9 million DNS answers to 1,593 different victims using 605 different queries to generate answers. The biggest day of the attack was February 1st, which was 180,000 queries during that day. If you take that 180,000 queries for the day, you multiply it by 30,000 reflectors, assuming they continue to use 30,000 reflectors, multiply that by your 32,000 bits per response, that comes out to about 180 terabits of attack traffic on February 1st. After February 15th, we saw a pretty big ramp down, and we lost all visibility in what was going on from this particular reflector. We don't think the attacks stopped. We think they changed a little bit. There were some well-publicized attacks, namely the WorldNick and Joker.com attacks that happened after that date that we had no visibility into. So if we look at this graph, the bottom graph of the bandwidth that the individual reflector sent out, and we multiply that by 30,000 reflectors, we can estimate the total attack traffic that happened during that duration. And you can see that there was a significant number of attacks between the 3.5 to 5 gig range, and one attack that got up to just over 7 gig. An attack of 7 gig, 220,000 packets per second is pretty consistent with some comments we've seen other organizations make about attacks they've made. The scary part is when you divide that out, the amplification factor out of that, it only took 130 megabits to generate that attack, the 7 gig attack, and the majority of the attacks were generated with less than 100 meg, which means 1 to 2 compromised, well-connected hosts in a data center could easily have generated all of these attacks. So what's the worst thing that can happen? How bad can this problem get? What happens if someone uses all 500,000 recursive DNS servers that are out there and keep the traffic levels the same per reflector, because it's a good number to stay under the radar? And we think that it's actually pretty easy to generate a 120 gig DDoS attack with this, using less than 2 gig of traffic to initiate the attack. So we looked at a distribution of the top 25 victims and the queries that they received over the duration of the attack, which is why this graph doesn't have a title, because that's a pretty big title. You can see that the top victim got about 130,000 queries over the duration, which again, you go back to the math of 30,000 reflectors, 32,000 bits per response. We think the top victim got over 130 terabits of attack traffic, and we think all of the top 25 are well over 20 terabits of attack traffic. When you look at the top ports that were used in this attack, you see something interesting. You look at this graph and you're like, wow, it's all DNS traffic, and that's what we thought too. And then we started looking at the math and something didn't add up. Less than 5% of the total attack traffic used destination port 53. The majority of it, 95% of it, was very well distributed across the 65,461 ports that were used. There are some interesting things in here though. The second most used port was 6667, which is used a lot by IRC. 666, which was used in the attack that we got to study. Some of the others in there. So this is the top 20 domains that were used and the relative frequency of how often they were used. This is kind of hard to read, but that's kind of on purpose. These are mostly innocent bystanders, so we don't really want to call too much attention to them. The xp.trc.cpc domain that was the subject of the NANOG thread that was very long on this is the most common. And the third most common was the e.tn.co.za that was the attack that we studied. And the scary part is that the second most common domain that's been used in this attack is the internet root dot. The scary part about that is you can't filter it. Most authoritative name servers will even answer with an upward referral for the internet root dot, which means that there's a significantly higher number of reflectors. And it's already being used. So when we look at trying to thwart this kind of attack, there are some fundamental challenges that we face. UDP lacks a three-way handshake, which makes it fundamentally vulnerable to spoofing attacks. DNS is a great target for this because there's a whole bunch of targets out there to use as reflectors. But other UDP protocols need to be looked at as well. Anything that's UDP needs to be looked at for a small query, large response pair. It's unlikely that a lot of these protocols will have a large enough install base to be used as a reflector. Now, when we talk specifically about the challenges of securing DNS as a protocol, with an estimate of over 500,000 recursive DNS server, closing that is going to be a very long and very painful process, especially when you consider how many people have poor separation between their authoritative and recursive DNS server. When you install one name server that does both functions, you have to answer queries from anywhere on the internet, and if you have recursion enabled, you're in a lot of trouble. You can do an allow recursion ACL, and that'll prevent the server responding for something that's not already cached, but it will respond with something that's already cached, and large commonly cached RRs could still be used to generate this attack, and there are some examples there of some ones that we think are pretty large that are pretty commonly cached. DNS servers that allow recursion shouldn't even accept queries from outside their network. They should use something like a bind allow query ACL to prevent this, their DNS server from being used as a reflector in this. And then the problem gets even harder because a lot of these aren't real DNS servers that you can actually secure. They're DSL modems and cable routers and SOHO firewalls that have DNS proxies that listen on the public interface by default. So that you just send a DNS query to your DNS modem, and your DNS modem will answer it. And another fundamental problem with DNS or fundamental challenge in dealing with DNS is that there are a number of technologies that are emerging and deployed that depend on larger and larger records in the DNS tree. RFID, DNSSEC, IPv6, enum, domain keys, SPF. These are all things that depend on large records of various types in the DNS infrastructure. So when we look beyond the open recursive DNS servers and we assume that, let's say, by some magic we actually managed to close the 500,000, the problem still exists. You've got the internet root dot that can be used for this. Now that's a 437 byte responsive memory serves, but every DNS server on the internet pretty much will answer for it. There's very few that don't. Now most of the authoritative name servers will only answer with the NSSAT, not include the actual IP address, so it's smaller, but you still get a pretty decent amplification factor. You go from like 63 to 1 to 8 to 1 if it answers with the full set, and it drops by half again if you don't include the A records. The biggest fundamental challenge is that there is no source validation on the internet that's real. IETF BCP38 is the real thing we need to do to fix this. Until we can stop people from spoofing the packet, we're going to be securing this. We dealt with this problem 10 years ago with IP-directed broadcast on all our interfaces and got Cisco to make that the default. And that was a problem 10 years ago, and now we're dealing with securing DNS, and tomorrow we'll be dealing with securing SIP or NTP or some other ubiquitous protocol that's vulnerable to spoofing. Really what we need to do is secure the edge and stop accepting packets from people that have no business sending them. Now there are some challenges with doing that. We don't believe that that's an easy problem to fix. You talk to an ISP, it's not doing BCP38, and they'll say, well, how am I supposed to manage 70,000 ACLs? Or what about my multi-home customers with static routes who are sending me packets from IP addresses I don't know that they own, but they do actually own? And what about people that have done things for years that haven't worked that should, like VPN tunnels that are sourced from private IP addresses on the inside of the firewall that magically work but shouldn't? RPF often gets brought up with BCP38. Strict RPF breaks with any type of traffic asymmetry, and loose RPF doesn't help in this case because the packets are sourced from addresses that really exist. Typically the answer you get when you talk to an ISP that isn't doing BCP38 about why don't you do it, and the answer you get is, well, it's a big problem, it's a long time to fix it, it's hard and it's expensive and I'm going to break things. And we absolutely agree that it is a hard problem to fix. However, if we don't ever start making progress on this problem, we're never going to fix it. And this graph on the bottom is just traffic we see from Belgons that have no business on the internet, but we see traffic from them on a daily basis. So in terms of going forward and recommended actions, closing the open recursive DNS servers is a good step. DNS software vendors should include filtering. I'm not sure which vendors do and don't include filtering, but everyone should, both in terms of allow recursion and allow query. You should be able to filter where you will even accept a query from. SOHO router vendors should start to do work to make sure that their DNS proxies by default don't listen on the outside interface. And really the only thing that will ever solve this problem is BCP38. Until we can stop the spoofing, we're going to be jumping from protocol to protocol over the next several years trying to thwart these kinds of attacks. So that takes us to the end of the presentation and questions. Typically one of the first questions I get is, what is VeriSign doing to protect the root and TLD infrastructure that we run to support this? So what we're doing is massively building out capacity in terms of adding Anycast servers and adding transit and peering capacity. So.
Hi, Jared Mach, NTT America. So in doing the transit for NANOG, I decided I would be evil and turn on unicast RPF on the interface. And it looks like there's about 372,000 packets that people who are here have generated that have failed the RPF check. So can you please clean up your machines?
So that brings up an interesting point with RPF and BCP38 that I forgot to mention. I understand that BCP38 is hard to deploy, and I think maybe if we don't have the features we need to work with our vendors to come up with better technologies to do it.
Okay. Well, I just wanted to sort of point it out as a data point. I'll try and get, Paul Quinn asked me what percentage of the traffic that is. I'll have to do some math and figure that out. I'm sorry.
Mike? Microphone, please. Thank you.
I was just wondering about the address ranges in the packet, and were you actually seeing any packets in the zero conf?
So,
I will tell you, just one second. Okay. My name is Bora Akil. I'm from Broadcom. Sorry about not saying it earlier. I just wanted to know if you had any data on the source ranges of the packets that you're seeing.
I could potentially look in the 1 in 10,000 sample net flow data that we have and look and see what I could potentially find over the couple days. But the, you know, so the individual link, it's basically a /30 point-to-point link. So to me, it just looks like a normal customer link like anything else. So I'm not seeing any extra broadcast traffic or anything else. So this is packets that are being sourced by people here and are going through the Merit router, which evidently they're not RPFing you either on their routers, so maybe they should do that as well. But this is traffic that people here in this room are dumping onto the internet as a whole.
Ren Provo, AT&T. Where are you planning to peer? When? And do you have your policies posted?
Not yet. We expect the first site to come live in the next 2 to 3 months.
Where?
Miami, Terramark.
Thank you.
There will be additional sites both domestically and internationally over the next year and a half. Done?
Unless there's any more questions, I think it's time for the next person.
Thanks, Chris.
Thanks, Frank.